Hello everyone again. I will be talking today about performance of the CFRP anchors and infill blocks in shear strengthening of I sections on behalf of my dear colleague Mohammed Arslan Yaqub. This research is part of his PhD thesis and he's mentored by Professor Krajnovic from Ghent University and Dr. Krajnovic from ANTA. First, I will talk about shear strengthening of I-girders, then some anchorages that are used in the past, then I will show the current experimental program and test the results, and I will end with conclusions. So the question is how to strengthen I-girder for shear, and the answers from the literature are that they are diagonal strips for strengthening I-girders, then vertical strips for strengthening I-girders, and continuous sheet for shear strengthening of I-girders. What these three configurations have in common is debonding around the web-flange corners of the I-girders. I will show some anchorages used in past. The first one is is simple horizontal strip in the web of the I section, and there are two studies, one from 2000 and one from 10 years later. And the first one shows increase in shear capacity of 35%, and the second from 15 to 27%. So this is when the vertical strips are anchored with the horizontal strip, and there is also the same way to anchorage the diagonal strip. In that case, the increase was 36%, and for the second study, 17 to 22%. The second way is to add the horizontal strips at the web-flange corners. And for the first study, there was no improvement, and for the second study, there was also no improvement of shear capacity. The third way is by mechanical clamping in the flange web corners, and the first study showed improvement in shear capacity of 28%, while the second study showed a little bit of inconsistency. The first test showed no improvement, and the second test showed improvement of 24%. The reason for this is probably you can see here CFRP raptors with the strength concentration and crack propagation through the anchorage, which can explain this inconsistency. The next one was near surface mounted anchors at the corners of the web-flange of I-beam, and here there was also an inconsistency. The first test showed 36% of the increase, while the second test showed no improvement. So the concern was that there is a stress concentration at the web-flange corners due to the growth hut. And finally, we come to the spike anchorages. Here we can see the vertical strip with spike anchors, and the increase is marginal, 2%. Then we see vertical strip with vertical strip plus spike anchors, and the increase is 36%. And finally, we see continuous sheet with 5 anchors, where the increase is 38%. There are the question, because here there are a lot of 5 anchors. Is it safe to drill anchor holes in the thin web of the eye girders? This can even reduce shear capacity. So now I will talk about the experimental program that is done by my colleagues at Ghent University. So prior to full-scale testing, they developed this alternative testing campaign on testing shear capacity of external reinforcement on medium scale, where they casted 10 slices of 300 millimeter wide and 300 millimeter long eye cross sections with the syrup and concrete of 60 megapascals and yield strength of the steel with 570 megapascals. So the syrup was in the middle of the eye section. So the specimen has a height of 700 millimeters, and there were 2 steel plates for artificial cracking introduced with the angle of 25 degrees. There was the 6 millimeters double-length syrup in the middle of the specimen, and there were 2 threaded bars for loading welded to the steel plate and fastened to the external steel plate, which is then which transfers load to the another steel bar, which was clamped into the testing machine. And when it comes to external reinforcement, there were CFRP strips unidirectional with width of 150 millimeters, thickness of 2 times 0.11 millimeters, strength of 4,400 megapascals, and fixation was with 5 anchors made of steel. So here you can see 3 strengthening configurations. The first one is around the eye beam without any 5 anchors. The second one was the same, but mechanical anchors were provided in the web-flange corner. And the third one is with infill concrete blocks glued with epoxy to the eye beam, and then U-shaped CFRP that was anchored with the carbon anchors in the compression zone. And here you can see first the control specimens, then the first configuration, then the second configuration already in the testing machine with the assist pattern, but you can see here 2 and here 2 5 anchors. And finally, you can see here the infill blocks combined with U-shaped CFRP, also in the testing. So different instrumentation was used. The load cell was used for monitoring the load. The 2 LVDTs are used. Then strain gauges on the CFRP strips, and 1 strain gauge on the internal syrup in the middle, and digital image correlation was used for monitoring of deformation response on the surface of the specimen. So let's see the test results. First configuration didn't show any improvement of shear capacity. So the cracking load was 25, and the ultimate load was close to 120, and it failed by debonding, but there was no improvement in shear capacity. We can see that the debonding was at the corner of web-flange. For the second configuration, there was also the debonding of the CFRP syrup at the upper web-flange through the anchors, and in this case, the increase was 13%. And for the final U-shaped configuration with infill blocks, there was also debonding at the sub-flange this time through the anchors, and the increase was 23%, the shear stress. So now I will show you crack opening. The crack opening was measured by two LVDCs on the faces of the specimen, and their average led to the crack opening at the middle. So here you can see the first two specimens behaved very in similar manner, and you can see here the effect of the anchor. And what I forgot to mention, there was a very high increase in cracking load for the third specimen due to the infill concrete blocks. And we also see larger crack openings due to the longer strained length of CFRP. Then we can see the strains at the level of crack. Here are the strains in CFRP. We see the high increase in the load, and then the cracking behavior. And for the third configuration, we see the high increase in the cracking load and different afterwards. So this was in the middle of the eye girder. Then we see the strains in the steel syrup. We can see it is monitored by one strain gauge in the middle of the specimen, and we can see the yielding of the steel here, and the different behavior with infill blocks. And because the test was the deformation controlled, we can see the strain compatibility on CFRP and on this steel level. So here you can see the strain fields at the peak load. For the first configuration, we see the strain development towards web-flange. For the second configuration, we see that the strain development is restricted here and here due to the spike anchor. And for the third configuration, we can see the lower strains in the anchored zone due to the larger density provided with the spike anchor. So here you can see the strain distribution along the height of the beam. For the first two configurations, we see the strain concentration at the crack and the strain development towards the web-flange corner. For the third configuration, we see the strain distribution over the total length of the specimen, and which facilitated higher, larger crack openings. And we see the fewer strains in the anchored region. So there were following conclusions can be made. The FRP shear strengthening configurations for the eye girders are susceptible to early debonding at the web-flange corners, requiring the proper anchorage. The device specimen configuration plus test setup proved to be effective for the comparative study of different shear strengthening strategies. The U-shaped configuration eliminated the debonding and exhibited high ultimate loads compared to equivalent I-shaped configurations, and I configurations that exhibited higher resistance against the crack opening, while U configuration showed higher ultimate load. This study is followed by a full-scale behavior of the IV inverters strengthened in shear, and this is recently published in their publication called Shear Strengthening of pre-stressed inverters using carbon fiber reinforced polymers and Intel concrete blocks, published in Structural Concrete. And here the reference used in this presentation. And I will welcome your questions. I will ask you to send your questions to my colleague Arslan. He will gladly answer them.